All right. Hello, class. This is a lesson for IB Physics SL. I hope everyone's doing well. I see there are 2 viewers right now. Maybe our 2 viewers could name themselves just so I know who's watching. And I'll watch the live stream, the live chat out of the corner of my eye. So what I would like to do is just start off with a little example from the stuff that we've been learning with circuits. Okay, so what I would like to know is what is the power output of the battery. We've got a circuit that has a 6-volt battery. Oh, hey, Christian. And we've also got a number of resistors. Okay, so I would ask you guys to actually tell me which connection is which and what's in series and what's in parallel, but there's about a 15-second delay, so I'm not going to do that. I don't want to wait around. But one of the things we can immediately see is that these 3 resistors are in series. So if I use the formula for series resistors, you just add them all up. So I got 1 plus 2 plus 3 equals 6 ohms for that resistor. Okay. I could redraw the circuit immediately, but I'm going to do one more. Actually, this 4 ohm resistor and that 4 ohm resistor are in parallel. So I can simplify those two as well. The formula for that equals 1 over 2. So that says that R sub P is 2 ohms. All right. Their total resistance is half. So you have 2 4 ohm resistors. Their total resistance is going to be half of that, which is 2. All right. If you have 3 equal resistors, the total resistance is 1/3. So if there were, 3 4 ohm resistors in parallel, that would be 4/3 of an ohm would be the total resistance. So that's just handy to know. You can always get the answer just by this formula. So I'm going to redraw the circuit. The 3 resistors, I'm going to replace it with 6 ohms. Okay. And then the parallel resistors I've replaced with 2 ohms. And then this is still 5 ohms. Okay. Okay, I'm back. Plus, so I'm not sure how much was cut out, but 1/6 plus 1/8 plus, and then the third branch in this parallel combination is 5 ohms, so plus 1/5. So if I add those up, so I'm using my calculator right now. I get that this is equal to 0.49. And if I do remember that is the inverse of the parallel resistance. So that means that R sub P equals 1 over that, 2 ohms. Okay, so this is basically, so if I simplify this to 1 resistor and 1 battery, it's just that. All right, but the original question was what is the power output of the battery? And the formula for power, actually I gave you 3 formulas for power. I gave you power equals IV, power equals I squared R, and power equals V squared over R. These last 2 ones were applicable to resistors, power dissipated by resistors. We've got 3 people now. I only know that Christian is 4 people. Whoa. Who's watching? All right. So anyways, I'm going to use this equation right here for the power because I know the voltage of the battery and I know the size of the resistance. Okay? So that would be 6 squared over 2. And that would be 36 over 2, which is 18. And if you recall, the unit of power is watts. All right. So that's just a little example to refresh your memory. Boom. So we're going to talk about something else today that Tim Chang is watching. Why is Tim Chang watching? You're not in IB physics. So at any rate, now we're going to talk about the new stuff for today. And basically the new topic for today is predicting resistance. Okay? And so when we're predicting resistance, well, basically you have a sample, and the sample has maybe a shape like this, and okay, so it kind of looks like this. Okay, so there's the sample, and the sample has a certain length, which we'll call L, and it has a certain cross-sectional area, which we'll call A. All right, and so you're imagining current, which is denoted by I, is kind of flowing down this wire, or this thing. So we want to be able to predict what is the resistance of this chunk of material, okay? And so there's a really nice formula, and it says R equals rho L over A, where L is the length of the sample, A is the cross-sectional area, think of it kind of like a freeway. If you have a freeway with a lot of lanes side by side, it's really easy to go down the freeway. So, and then this is the Greek letter rho. And the Greek letter rho stands for something called resistivity. So resistivity is different from resistance. Resistivity is a property in ohm meters. Okay. And so let's go ahead and see how that works. Let's do an example problem. And once I'm done with this example, I'll be done for the night. And I'll go over to the Discord and answer any questions anyone has. Hey, Ben's here. Hey, Ben. Okay, so let's say we have a copper wire is 600 meters long and has square cross section of side length. Let's say L equals maybe 4 times 10 to the minus 3 meters. Okay, so it's a square. It's kind of like this. Okay. And this would be 4 times 10 to the minus 3. And this would be 600 meters. So, first thing we have to do is we have to figure out what is the resistivity of copper. So let me show you how to do that. Check it out. Let's see if this works. That work? Cool. Resistivity of materials. And so that takes me to a bunch of web pages that have resistivity of different materials. So I can look it up. Here's an image. And let's see. It says, am I back? All right, I think I'm back. I'm back. Okay. So anyways, that's the resistivity of copper. I just looked it up. And so that's going to be useful to us. Just use the equation, length of a side in the square. So that's actually going to come into play in the denominator. So the area of a rectangle is length of a side squared. So it's going to be divided by 4 times 10 to the minus 3 squared. Resistivity is 1.7 times 10 to the negative 8. And the length of the sample as a whole is 600 meters. So this many ohms, however many ohms that is, probably not very many because copper is a good conductor. I should say that materials that have small resistivities are good conductors. Okay, you could make a resistor out of copper, but it would have to be very long and it would have to have a very small cross section. But if the resistivity is small, we would say it's a good conductor. All right, so I would expect you to be able to do that kind of calculation. The thing that could change might be the area. It might be a circular cross section. It might be a triangular cross section. It could be anything. That's really the only thing that can change.